Hello all, my name is Ashutosh Rastogi. I am a teacher by profession. My mission is to impart quality education for all. For that purpose I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos.
Anyways, today in this particular lecture, we will going to discuss about the performance parameters of direct sequence spread spectrum systems. These are the outlines. We'll start up with the introduction. Then we will going to discuss about performance parameters for direct sequence spread spectrum system, such as processing gain, probability of error, and jamming margin. What are they? What are their basic definitions? Then we will going to discuss a numerical problem related to the performance parameters of direct sequence spread spectrum system, where we have to evaluate all those performance parameters and get the better understanding about the performance parameters for direct sequence spread spectrum systems. So in our last lecture, we have discussed about the direct sequence spread spectrum systems. We have discussed how to generate direct sequence spread spectrum signal with the help of PN sequence generator. We have also discussed several applications of direct sequence spread spectrum communication systems. So performance parameters gives the information about the behavior of any system. What do you mean by the behavior of any system? They basically gives the information that how a particular system behaves, whether it is performing up to the mark or it is lagging in performance. So obviously, in order to measure the performance of any system, there has to be certain parameters that we have to measure. So in this particular lecture, we will going to discuss the performance parameters of direct sequence spread spectrum systems. So the performance of direct sequence spread spectrum system have been measured on the basis of these parameters. They are processing gain, probability of error, and jamming margin. We will going to take up one by one. So first one is processing gain. Processing gain is the measure of how much spreading has been performed in the bandwidth of the signal. We had already seen that in spread spectrum communication system, we are spreading or enhancing or expanding the bandwidth of our baseband signal. And the processing gain would have been defined as the ratio of the signal bandwidth after spreading to the bandwidth of the signal without spreading. So processing gain is the ratio of bandwidth of the spread spectrum signal to the bandwidth of the unspreaded signal that we have already studied. So processing gain would have been denoted with this GP, and it is equal to the bandwidth of the spread spectrum signal or the bandwidth of the signal after spreading divided with the bandwidth of the signal without spreading or unspread signal or signal in its purest form. In our last lecture in the baseband model of spread spectrum system, we have seen that the spread spectrum signal or the spreaded signal MT would have been calculated as the product of the data signal BT with the spreading code or the chipping sequence code CT. So after multiplying these two signals, that is our data signal BT and spreading code CT, we are having our spreaded signal MT. So here this TB denotes the bit duration and this TC denotes the chipping duration. And one more point should have been clear that in a complete TB duration, there are capital N number of chipping sequences have been lying. So the relationship between the TB and TC turns out to be TB is equal to N times of TC, which is very much clear from this particular figure. So this is basically our transmitter waveform. We had already discussed that in our last lecture. We have seen the spread spectrum signal MT that is obtained by multiplying both the NRZ signals BT and the CT, where BT is the bit sequence and CT is the chipping sequence. The 1 minibit, that is chip period, of the spread spectrum signal MT is given as TC, and hence the bandwidth of the NRZ signal is the reciprocal to its 1 bit duration. As we all know that for NRZ signal, the bandwidth would have been evaluated as the reciprocal of its bit period. Therefore, the bandwidth of the spreaded signal MT equal to 1 over TC, where TC is nothing but the chipping duration. So in the similar manner, the bandwidth of the unspreaded signal or our signal in the purest form would have also been calculated as the bandwidth of the unspreaded signal BT will be equal to 1 over TB, where TB is the bit duration. Hence, the processing gain would have been evaluated as, since it is the ratio of bandwidth of the spread spectrum signal to the bandwidth of the unspreaded signal. So this GP would have been calculated as 1 over TC, which is the bandwidth of our spread spectrum signal to the bandwidth of our unspreaded signal, which is equal to TB over TC. Here one should be clear that GP is almost equivalent to TB over TC, since we are approximating the bandwidth of our spreaded signal to 1 over TC, although it is actually equivalent to 1 over TB plus 1 over TC, as we had seen in our last lecture. So GP is almost equivalent to TB over TC, but TB over TC is equal to N. Hence, the larger value of N PN sequence gives the higher processing gain. So obviously, the larger value of N will going to give the higher processing gain. Obviously, both of them have direct relationship, but as we mentioned that GP is almost equivalent to N, as we are approximating the bandwidth of spreaded signal from 1 over TB plus 1 over TC to 1 over TC only. Next performance parameter is probability of error. So for the coherent BPSK system, the probability of error would have been given as 1 upon 2 ERFC under root of EB over N naught. Here ERFC representing the complementary error function. Here EB is energy per bit and N naught upon 2 is the noise power spectral density of white noise. So in direct sequence BPSK system, the interference may be treated as a wideband noise signal with power spectral density of noise, since we are spreading our signal bandwidth, and we have seen that keeping the signal power constant and expanding the signal bandwidth, the power spectral density reduces very much. So since we are expanding our signal to wideband, so its strength will automatically become lower. So that lower PSD signal would have been considered as the noise-like signal. So that is why we are saying that in direct sequence BPSK system, the interference may be treated as a wideband noise signal. Therefore, N0 upon 2 will be equal to I times of TC over 2. So since N0 is the noise power spectral density, so that will be equal to I times of TC upon 2. It implies N0 is equal to I times of TC. So where I is the average interference power, and since we have to talk about the noise power spectral density, so the power spectral density is nothing but it is the ratio of noise power to the bandwidth of the signal. So since the bandwidth of the signal will be equal to 1 by Tc, so finally we can write it as I times of Tc. So the final expression for noise power spectral density turns out to be I times of Tc, where I is the average interference power and Tc is the chip duration. So now putting the value of noise power spectral density N0 in the expression of error probability, we have E turns out to be half of complementary error function under root of EB over N0. At the place of N0, we have placed this value I times of TC. So the complementary error function is monotonically decreasing function. Hence, the error probability decreases as the SNR increases. So monotonically decreasing functions means it will going to continuously decrease. Any point of time, its value will not going to increase. It is continuously decreasing function. So obviously error probability will going to decrease as the SNR will going to increase. So now the last performance parameter is jamming margin. Energy per bit would have been given as EB is equal to P times of TB, where P is the average signal power and TB is the bit duration. As we know that the relationship between the energy and the power is nothing but it is energy per unit time. So energy would have been written as product of power with the time. That is why we have written as EB is equal to P times of TB. So we can express the bit energy to noise power density ratio as EB over N0 turns out to be P times of TB over N0. So EB over N0 we have written in terms of power and bit duration. So it turns out to be P times of TB upon N0. But we know that noise power spectral density will be equal to I times of TC, where I is the average interference power and TC is the chipping duration. Therefore, we can write EB over N0 will be equal to P times of TB over I times of TC. We have replaced this N0 with this I times of TC, which could further be rewritten as EB over N0 will be equal to TB times of TC. So we just have taken these two terms together and again taken these two terms together. So TB over TC multiplied with P over I. But we know that TB over TC is nothing but our processing gain. So this could have been again written as TB over N naught is equal to GP, that is your processing gain, times of P over I, where P is the average signal power and I is the average interference power. So from the last expression, we could also evaluate the value of I over P. That turns out to be GP over EB by N naught. So this ratio, interference power to the signal power, is actually being known as the jamming margin. So the ratio I over P is called the jamming margin, which is defined as the ratio of average interference power and the signal power, and is denoted as MJ, where M denotes the margin and J stands for jamming. So jamming margin, that will be equal to I over P, that is equivalent to GP over EB by N naught. So if both the jamming margin and the processing gain is represented in dB, then we could write this expression as jamming margin in dB is equal to processing gain in dB minus 10 log EB by N naught minimum to the base 10. So here EB by N naught minimum is the minimum bit energy to noise density ratio needed to support the given error probability. So this basically describes the formal definition of jamming margin. Jamming margin is nothing but it is the capability of any system to accept the interference power and giving the same performance as bit error rate while decreasing the EB over N naught ratio. So we should focus on this particular formula. Jamming margin in dB will be equal to processing gain in dB minus 10 log EB over N naught minimum to the base 10. So now we're going to discuss the numerical problem. So a spread spectrum communication system is characterized by the following parameters. What are they? Bit duration TB will be equal to TB is equal to 4.095 millisecond. Chip duration of PN sequence TC equal to 1 microsecond. Then calculate the processing gain and jamming margin if EB over N naught is equal to 10 and the probability of error PE is equal to 0.5 into 10 to the power minus 5. So for these given values, we have to calculate the processing gain as well as the jamming margin. So in order to solve the numerical problem, so our strategy is first to write down whatever the values are known to us. So given that TB is equal to 4.095 millisecond and TC is equal to 1 microsecond and PE, or we could say the error probability, that is equal to 0.5 into the power minus 5. So all these three values are known to us. We know the processing gain is given as TB over TC. So we know the value of TB as well as TC. Now putting the values of TB and TC in the formula, we have 4.095 into 10 to the power minus 3, since we have 4.095 milliseconds, and 1 into 10 to the power minus 6 as TC is in microsecond. So finally GP turns out to be 4095. So the value of processing gain will be equal to 4095. This is our first answer. So now the jamming margin in dB will be equal to processing gain in dB minus 10 log base 10 EB over N naught minimum. This is the formula that we have discussed for jamming margin. So now the formula would have been written as MJ, that is your jamming margin in dB will be equal to processing gain in dB minus EB over N naught expressed in decibels. So jamming margin in dB will be equal to 10 log 4095 to the base 10, since it is the value of our processing gain, minus 10 log 10 to the base 10. So by the logarithmic property, we know that log of any value to the same base will be equal to 1. So here log 10 to the base 10, its value will be equal to 1. So what we are left with, jamming margin in dB will be equal to 36.10 minus 10. So the value of this 10 log base 10 4095 would have been evaluated as 36.10, and the value of 10 log 10 to the base 10 will be equal to 10. So now after evaluating this expression, we are left with 26.10 dB. So the jamming margin in dB would have been evaluated as 26.10 dB. This is our final answer. One has to be very careful while answering the numerical problems. The care must have been taken about what it has been asked in the question. So here we have evaluated the value of jamming margin in dB. Since it hasn't specified in our question that whether we have to calculate it in terms of dB or in linear, so if nothing has been mentioned, then you can evaluate in any form, that is in dB or linear. But if it has specifically asked in dB, then you have to evaluate in dB. And if it has asked to calculate the linear value, then you have to evaluate its linear value. So conversion is quite simpler. If we want to convert this 26.10 dB into the linear one, then we can write 10 log base 10 x will be equal to 26.10. The x value would have been calculated as 10 to the power 2.610. So that will be our answer in linear scale. But since in this particular problem nothing has been mentioned strictly, so we have our answer as 26.10 dB. So these are the references. Thank you very much for your patience.